Good morning and welcome to today's webinar. My name is Keira Proctor and I'm the Managing Director of the A. Proctor Group Limited. And today we're going to revisit our look at the basics of building physics and then take a look at the latest membrane-related developments in the BS 5250 Code of Practice for the Control of Condensation. This is the 12th in our series of webinars since lockdown in April, and whilst I hope everyone is getting back towards normal now, you can still go back and view the whole series on demand via our YouTube channel or our Learning Hub at www.proctorgroup.com. There you can also book an online CPD or a virtual meeting with one of our team. As always, we'll be having a Q&A session after our main presentation, so if you have any questions you can type them into the chat box, or if you prefer, email them to webinar@proctorgroup.com or send us a DM on Twitter @proctorgroup. Here at Proctor's, we focus for a long time on the importance of good design to manage the movement of heat, air and moisture around the building envelope. So today's webinar looks at some of these interactions and how we can best manage them. In order to design structures that are energy efficient and healthy to live and work in, designers have a clear need to balance the heat, air and moisture movement throughout the building envelope. So, understanding these elements and how the interactions between them work is an increasingly important factor in ensuring today's highly optimised buildings are fit for purpose, not just today, but for many years in the future. So to begin, let's review the basic factors relating to heat, air and moisture movement, starting with heat transfer. In terms of energy performance, managing heat transfer is the most obvious consideration in our design process. There are three basic models of heat transfer that are present in all buildings to some extent: conduction, convection and radiation. The simplest way to illustrate all three is heating a pan of water on a hob. Conduction. Conduction happens where two objects are in contact with each other, like the base of the pan sitting on the hot plate. This direct contact lets the heat flow from the warmer hot plate to the colder pan, either until the temperatures equalise or the pan is removed. Most building insulation boards, such as mineral fibre, polyurethane, for example, work to resist heat transfer by conduction. Convection. Convection occurs when heat is transferred by a fluid medium, which in buildings is usually air, but in our example here is the water in the pan. As the water at the bottom of the pan heats up, its density reduces and the warmer water will rise relative to the surrounding cooler water. The cooler water then sinks to take its place, setting up a circulation of water known as a convection current. As the temperature of the water becomes more uniform, the speed of current will reduce. In buildings, convective heat transfer can be minimised by ensuring good air tightness is achieved, restricting this circulation from happening. Radiation. Radiation is the transfer of heat from one material to another, which occurs by means of electromagnetic waves. Radiation does not require either physical contact of the materials or a fluid medium. A warm surface such as our hot plate will emit infrared radiation, which can travel across a space, even in a vacuum. When these infrared waves strike another object, they are converted back to heat. The efficiency of this conversion process is governed by a property called surface emissivity. The lower this value, the less able a material is to absorb or emit heat via radiation. In construction, reflective foil membranes and foil-faced insulation materials can help limit heat transfer by radiation. So those are the basic mechanisms of heat transfer, but now let's move on to the specific properties materials have and how they influence the design choices we make. The most relevant material properties to our discussion today are thermal conductivity, thermal resistance, thermal mass and thermal transmittance. Thermal conductivity. The thermal conductivity, also known as the lambda value, or K factor, is measured in watts per metre Kelvin and tells us how well a material lets heat flow through it at a given temperature. The lower the conductivity, the better the material will restrict heat losses. In our example here, you can see that the high thermal conductivity steel beam on the left quickly transfers heat from the burner. This is because steel has a relatively high conductivity at about 50 watts per metre Kelvin. On the other hand, in the concrete beam on the right, it takes a lot longer for the heat to reach the top side of the beam. The K value of concrete is much lower at around 1 watt per metre Kelvin. Materials commonly used as insulation are lower still, typically in the range of 0.015 to 0.044 watts per metre Kelvin. Thermal conductivity is useful for comparing materials as it does not account for thickness, making a straight comparison of how good is the insulation easier. It's less useful, however, when we need to consider a specific application, such as roof or wall, as it doesn't account for how much material we're using. If we want to include thickness as a factor, we need to look at the thermal resistance, or R value. This is measured in meters squared Kelvin per watt and is calculated by dividing the thickness of a material in meters by its thermal conductivity. For a given material, the thicker a block we use, the higher the R value will be, and therefore the greater its insulating effect. Thermal resistance is directly proportional to thickness, so looking at the 2 blocks of concrete shown here, if we halve the thickness of the block, we will double the rate of heat flow through it. Thermal mass. As well as how materials respond to heat flow, their capacity to retain heat is also important. This is governed by their thermal mass, also referred to as fabric heat storage. We can see here how the low thermal mass steam beam cools down quicker than the high thermal mass concrete. In buildings, this property can be used to even out temperature swings and maintain a consistent temperature with less heating or cooling energy input. The final property we need to consider here is the thermal transmittance, or U value. The U value of an element is the inverse of the sum of all the R values in a construction and gives an indication of the heat flow through a given element, in this case a wall. In practice, though, the R values for each layer need to be adjusted to reflect things like air gaps and structural elements like studwork. Locations where structural elements intersect insulation are known as thermal bridges, and in these areas, heat typically flows faster than through the insulation. U values are therefore adjusted to reflect this, and the methods for doing this are given in the ISO 6946 standard and the BRE guidance document, BR 443. Non-repeating thermal bridges, such as floor and roof junctions and corners, are also adjusted for. The heat losses associated with these features are called psi values. Where these bridges occur, the temperature in the element will be lower, and if they are not properly designed, cold spots can occur internally, which can lead to condensation problems, both on the surface and internally. If and where condensation will occur in an element can be predicted by looking at the dew point temperature. We can use the R values for the layers in the element to produce a temperature gradient graph. From this graph, we can then use a combination of the internal and external environmental conditions and the vapour and thermal resistances of the layers within the construction to produce a corresponding dew point graph. Provided the actual temperature gradient through the structure remains above this dew point line, no condensation will form. However, if the dew point and temperature gradient graph lines intersect at any point, then condensation will occur. We'll come back to condensation and other moisture sources later on, but for now, let's consider air movement in structures. It's important here to note that what we're talking about is unplanned air movement. Planned air movement, provided by ventilation systems, is an important part of maintaining good indoor air quality. So when we talk about air tightness, we really mean unintentional air openings and the uncontrolled exchange of air from outside to inside and vice versa. This can have a significant impact on the overall energy efficiency of a building, and as fabric insulation levels increase, this becomes an increasingly influential factor. The 2 basic factors affecting air movement are infiltration and exfiltration, air moving in and air moving out of the envelope, and there are various mechanisms which drive this. The 3 main air pressure phenomena affecting air movement are stack pressure, wind pressure, and mechanical pressure. Stack pressure. The first, stack pressure, arises from the stack effect in the building. This is an important driving force behind passive ventilation strategies. However, if not properly designed for, it can lead to air leakage problems. Stack pressure is caused by the convection current we discussed earlier, where warmer air rising through the building draws cold air in at lower levels. This creates pressure gradients as shown, from outside to inside at the lower levels and from inside to outside higher up. This effect becomes more pronounced the taller the building gets. Wind pressure. The second, wind pressure, results from a difference in pressure between the windward and leeward sides of the building. The positive pressure on the upwind side pushes from outside to in, and the negative pressure downwind draws internal air outwards. Being driven by weather, the directionality and extent of this pressure can vary considerably. We also have to consider the effects of shelter provided by surrounding structures and any variations that may occur between the upper and lower stories of a building. Mechanical pressure. The final air pressure driver is mechanical pressure, associated with ventilation and air conditioning systems. In high-rise residential and commercial structures, large-scale air handling equipment is capable of creating substantial pressure drops within the building. Natural sources produce pressures of up to 10 pascals, while mechanical systems can go as high as 60 pascals. If this is not managed correctly, it can contribute by drawing air into the building envelope from unintended sources. Additionally, if the system is not installed well, leaking ductwork may draw air into the system that has not been accounted for, with a corresponding detrimental effect on the efficiency of both the system and the building as a whole. So the common factor across all these mechanisms is the presence of holes in the building envelope, through which uncontrolled air movement can occur. This air movement can not only significantly reduce the energy performance of the building, but introduces a discrepancy between the as-designed and as-built performance that can lead to complex and expensive remedial action. It's therefore important to ensure that the air barrier system used is robust and flexible enough to perform as designed, both initially and throughout the building's life. Traditionally, air barrier membranes have been installed internally on the warm side of the insulation. Typically, these also function as vapour control layers. This positioning requires the air barrier to be sealed at all surface and structural penetrations and remain sealed. If the membrane is damaged either during installation or following trades at later refurbishments, for example, then both air leakage and moisture vapour ingress problems can arise. If care is not taken to seal all external elements effectively, this can also allow cold air movement around insulation, known as thermal bypass or wind washing, which can lead to reduced energy performance, cold spots and condensation issues, particularly if there are continuity issues with the airtight VCL line. By moving the air barrier to the cold side of the insulation, external systems such as our Wraptake allow for an almost penetration-free airtight layer, which can be installed faster and more robustly. Far simpler than internal options, the Wraptake external air barrier system maintains the envelope's integrity with less building surfaces and structural penetrations to be sealed and less room for error. Being fully self-adhered to a substrate is also better able to resist external forces such as wind loads, ensuring good performance is maintained by minimising wrinkles and poor sealing. External systems require good vapour permeability to ensure moisture is not trapped within the construction, and this opens up a third possibility. This is to position the air barrier layer within the construction, over the structural sheathing board, but behind the outer layers of the thermal insulation. This increases the protection to the air barrier layers and can help simplify detailing of the membrane. Care must be taken with this method to ensure wind washing through the outer insulation does not occur, for example with use of a vapour permeable jointing tape on the insulation boards. An internal air barrier is only as good as its installation. If all the surface penetrations are not adequately sealed, performance will be compromised. Switches and sockets represent the more obvious paths for air leakage, but there are many others which may be unseen. A huge variety of airtight accessories will be required when using an internal air barrier system. Example of these will include the airtight VCLs, pipe and cable gaskets, junction boxes, extractor fans, switch boxes, light fittings, and sealing tapes, to name a few. These airtight accessories are generally more expensive compared to standard non-airtight versions and take more time, care, and attention to install correctly. There can also be supply chain issues acquiring these products at short notice. In contrast, external systems generally require far fewer components and do not require as complex an installation process, leading to faster completion of the airtight envelope with fewer potential delays and construction errors. The increased speed of achieving airtightness means pressure testing can be carried out earlier, potentially simplifying any remedial action that is required. Combining these benefits in turn allows stricter air design leakage rates to be used, with greater confidence that the lower air leakage rates can be achieved. So now let's consider the benefits of this more reliable air leakage performance. If we can be sure we'll achieve a low rate of air leakage, then we can reduce the design air leakage rate used in our modelling, which means we can reduce our requirements in other areas. In a recent project we were involved in, this improvement in air leakage was traded off against the fabric insulation. In this case, however, the goal was not to reduce the thickness, but to switch from a rigid foam insulation to a less combustible mineral fibre product. Ordinarily, this swap would increase the thickness of the wall assembly significantly, but here, the reduction in emission rate delivered by Wraptake allowed this switch to happen with almost no additional thickness. This delivers cost savings across the building envelope, as depths of flashings, fixings and various trims can be reduced across the entire facade. So while a high-performance product like the Wraptake may appear more expensive at first glance, when we factor in the decisions and trade-offs it enables, it is not as straightforward as it may appear. The final element affecting our building design is moisture management. Controlling and managing the moisture flow in a building is fundamental to the core principles of HAM and also to maintaining the durability of the building envelope, maximising energy efficiency and protecting the health and the safety of the occupants. There are a number of potential moisture sources affecting all building envelopes, the most obvious being the external environment, weather and rain. Most rain screen systems commonly used in high-rise residential and commercial construction are not designed to provide a complete barrier to water ingress. Therefore, the cavity behind should be provided with the provision for drainage to the outside, and care should be taken at design stage so that water may not track into the inner layers. As well as for allowing for the drainage of liquid water, rain screens should be designed to ensure moisture from the interior of the building can escape and that any wetting associated with water ingress through the outer rain screen can dry out. This is typically achieved by fully ventilating the void between the outer cladding panels and the inner leaves of the wall. By ventilating, we ensure moisture vapour from all sources can escape freely to the outside. However, it does also mean that achieving a good airtight seal of the inner leaf is critical to minimise air leakage. A well-designed weather-tight layer is only as good as its durability, and a carefully designed rain screen that cannot resist damage will be limited in its usefulness. Internal moisture sources must also be considered. Achieving an effective and efficient moisture strategy depends on the design being carefully matched to the building's function. The same office design that works for an office may not work well in a sports centre, for example, at least not without significant over-engineering and added costs. Developing a thorough understanding of both how the building as a whole and specific areas within the building will be utilised by its occupants and the corresponding moisture production is key to achieving a robust and cost-effective design. Wet trades such as plastering and screeding and wet materials such as concrete also contribute significant quantities of moisture to the building envelope, which will evaporate to the internal atmosphere in the initial period following the building's completion. This is known as the drying out period. During this period, problems can arise even in buildings that have been well designed to accommodate their moisture loading, as the vapour pressures within the envelope can get significantly higher than normal. Condensation arising from this excess moisture can still cause damage to the building fabric, even if it only occurs for a short period after completion. As well as understanding the sources of moisture, it's important to understand how moisture moves around the building. Vapour diffusion is the movement of vapour molecules through porous materials because of vapour pressure differences. These vapour pressure differences are created because of temperature and humidity differences in the air on either side of the material. Most building materials are unable to stop vapour diffusion completely, and therefore building science uses the term vapour control layers, suggesting that they will control, i.e. slow down, the process, but will not completely prevent the movement of water vapour. Low permeability materials are those which can significantly slow down vapour diffusion. Transfer by convection occurs when airflow acts as a transport mechanism, carrying moisture in or out of buildings. Holes, cracks, penetrations and leaky ductwork may all provide potential pathways for moisture movement. As the moisture passes through the building, it will condense on surfaces with temperatures that are below dew point. Condensation levels will be affected by the difference of temperature between inside and outside, relative humidity and the speed of air movement. Moisture can also be transported by capillary action. This describes the ability of water to travel up through a building or material against the flow of gravity, like for example how water will wick up through a paper towel following the direction of the fibres. Capillary action works best with smaller pores rather than larger holes. For example, the fine pores found in brickwork or concrete provide an excellent mechanism to be used for this wicking action. In order to avoid the occurrence of excessive condensation, which can result in mould growth and damage to the building fabric and/or contents, designers should assess the amount of water vapour likely to be generated within the building and determine the resultant increase in internal vapour pressure above that of external air. They should then consider the physical properties of the construction, separating inside from outside, and how this interacts with the various moisture sources present. Lastly, designers should consider the effects of the external climate, which, being site-related, is beyond direct control, but may be moderated by the building's form and orientation in relation to topography, prevailing winds, sunlight, and overshadowing. Moisture and condensation can lead to mould and bacteria growth, which, if left uncontrolled, can have a significant impact not only on the fabric of the building, but also on the health and safety of its occupants. Assessing heat, air, and moisture. Now we've looked at all the foundation elements of heat, air, and moisture in buildings, we can begin to appreciate how to balance these effectively and how we can ensure this balance is achieved at the design stage. A basic principle here is to ensure that all factors we've already discussed are properly accounted for to ensure that the building envelope performs as intended throughout its life. Calculating the intricacies of heat flows and energy performance can be accounted for using a variety of modelling tools, from simple U-value and SBEM calculations through to complex BIM models and advanced simulations. The degree of modelling complexity required will vary from one project to the next. Depending on the system used, these models can account for everything from basic insulation levels to complex life cycle assessments and allow comprehensive optimisation of the building design by accounting for all these factors we've discussed. As well as our comprehensive technical support service, here at the A. Proctor Group we make BIM objects available for a range of our products, enabling easy integration into whatever design workflow you choose. In addition to fully modelling the energy performance, we must also make sure we properly assess how the building design balances moisture. Balance in this context meaning we must ensure that all moisture associated with the building can dry out, and that any moisture accumulation or wetting is balanced and equalled during the life of the building. As with energy modelling, it's important to use the right design tools. Traditional methods of assessment have in the past been based on the Glaser method. We talked a bit about this in last week's webinar on refurbishment, but it's worth reiterating as it's also relevant in a new build context. Developed back in 1958 for use in lightweight buildings, the simplified calculation used by the Glaser method is based on average monthly temperatures, vapour pressure, and steady-state conduction of heat to determine if critical condensation points are reached within 1 year. The limitation of this approach is that Glaser assumes vapour moves only one way, from inside to outside. It also completely omits the key feature of driving rain from its calculations, does not measure absorption or porosity, and therefore fails to identify potential risk attributed to the aspect of moisture storage. While this basic model is acceptable in some cases and useful for providing a rough guide to avoiding the worst and most obvious problems, a proper assessment of the wetting and drying balance of structures requires a more substantial approach. Outlined in the EN 15026 standard, this enhanced approach dynamically predicts moisture movement and storage as well as condensation for each location, taking into account climate effects such as driving rain and solar gains. The most common software used to assess structure via this method is known as WUFI. Using this modelling means the designer can achieve a minute-by-minute prediction over a given period of years, which provides invaluable when assessing the correct position for high-performance vapour control and vapour-permeable membranes to ensure a healthy building fabric. We can see from the example here that the Glaser method calculation simply shows that no condensation risks are predicted within the construction. A more comprehensive assessment with WUFI shows the rate at which construction moisture is drying out from the wall. We can also examine the differences between the placement and specification of various components within the wall. Here we can see the difference in drying out periods between internal and external placements of insulation. Placing insulation externally leads to a much faster reduction in the moisture contents in the masonry compared to placing it internally. So although there's no problems predicted using the Glaser method, WUFI clearly shows a better hygrothermal balance is achieved with external insulation over a longer period of time. The latest code of practice for the control of condensation, BS 5250-2011, incorporating the 2016 amendments, details when it is more appropriate to use EN 15026 or WIFI software and when the simpler Glaser method is acceptable for various types of building element. It is, however, clear that for more complex scale structures, a more dynamic and extensive approach enabled by using the latest software and improved computing power is not only desirable but more widely achievable than ever. Between WIFI moisture assessment and the more complex energy modelling enabled by modern BIM software, it's now possible to model the balance of heat, air and moisture accurately and hence to design and specify with much finer tolerances. This helps ensure a cost-effective and robust building that remains fit for purpose for many years. BS 5250 is the code of practice for the control of condensation in buildings and is referenced heavily in the building regulations in both the UK and Ireland. BS 5250 is therefore the fundamental basis of moisture control in building design. The current issue is 2011, incorporating 2016 amendments, but last month the public consultation document on the next revision was released, and while it's not in effect yet and may be revised following the consultation, it's worth considering some of the proposed changes now. The most obvious change is the title of the document, where before the title referred to Control of Condensation, the 2020 draft refers instead to Management of Moisture, reflecting an increasing holistic approach incorporating all sources of moisture that may be present. BS 5250 defines a lot of the terminology we use, and those definitions are frequently altered with each new update. The first addition in the definition are the concepts of ABIS and ADT conditions, standing for As Built and in Service and As Designed and Tested, respectively. This is important as there are often significant differences in the performance of the building envelope on paper. Regular viewers of our webinars will have seen this distinction come up a few times, and ensuring the correct materials are used in the correct way is a big part of closing the performance gap. The new draft also adds more detail regarding the airtightness of ceilings, with definitions for both normal and well sealed. While this definition and its related requirements were in the 2011 edition, the specifics were contained within the separate BS 9250 rather than included directly. Specifically related to membranes, all performance characteristics are quoted primarily in SD values rather than the older vapor resistance figures, and some of the definitions have been expanded and clarified from the previous drafts. The principal changes where membranes are concerned, however, are in the appendices detailing wall and roof constructions. In Appendix K covering wall constructions, vapor-permeable air barriers like our Wraptake membrane are incorporated, including their use with additional external layers of insulation. This recognises the benefits of utilising this type of membrane to simplify the reduction of air leakage rates. In roofs, Appendix L introduces a new construction type for non-ventilated roofs with air-permeable low-resistance underlays, APLR, under Section L5.4. While this type of construction was always allowed via third-party certification, this is the first time the benefits of air permeability in terms of condensation risk has been specifically addressed by the standard. This is further reinforced by the design flowchart provided in Figure L11, which highlights that APLR type underlays such as our roof shield are always acceptable in any configuration of roof. This is particularly noteworthy where ceilings are not well sealed and no vapor control layer can be provided, a common scenario in re-roofing projects and historic building work. We're going to take a look at roof design for both warm and cold pitched roofs and go into it in a bit more detail on BS 5250 on our next webinar, so keep an eye out for that. So now let's move on to the Q&A section.
Hello.
Good morning, everyone. I want to thank everyone for attending our another of our webinars. I'm going to stop calling them lockdown webinars because hopefully we're seeing that lift and coming out of it somewhat. And the good news is my cat Miles, who gate crashed our last webinar, is not joining us today. He's locked in the utility room, so he won't be making an appearance. So we're safe from the meows for now. Thank you very much for attending. Just some information first, and then I'll be able to introduce the individuals who are here to take the questions. You can request the product sample pack, or regarding the materials that were discussed during this webinar, or request a meeting with one of our staff. If you go to the web page that you registered on, so it's the webinar page, www.proctorgroup.com/webinar, you can do those things there. And personalised CPD certification is also available. So please fill out the online form and we'll get that sent to you. We love getting your feedback. We do read all of it, I read all of it, and we do take it on board, and we make changes to the future webinars based on some of the feedback, which has been super helpful. So if you have time, when you receive a follow-up email to this, which will be just after the webinar is finished, there will be a short survey. Fantastic if you can fill it out. There'll also be a link to a replay. So if you want to circulate that to colleagues, please do. We know that a lot of people are live on the webinar, but also we get a lot of views afterwards. So please feel free to circulate it to anyone who you may find it useful. And if you're watching this at a later date, then also welcome. It really helps us if you give us a thumbs up or you subscribe to our YouTube channel, and that will also keep you informed about any new webinars that you happen to miss on email or LinkedIn and the various different places that you can. You can find out the info for them. So yeah, it's doing really well. A lot, changing environment at the moment in the UK. Businesses starting to come back, and a lot happening. So I hope everyone's doing good. We'll be here to answer all questions sent. We do this every week. To say as long as we can. So please send them by email to webinar@proctorgroup.com. You can also post them in the YouTube chat box, which I can see some coming through quick and fast, which is great. Or you can DM us on Twitter @proctorgroup. So I'll just go through some of the familiar faces first, then introduce our special guest who's joining us. So Ian Fairn is our technical director. If you can just say hi and give us a wave, Ian, so we know you're all working. We can hear you as well, hopefully. Good. I think I heard a giggle. Yeah. Thank you very much. So Ian's our technical director, been with us for many years. Sue Menmure is our technical advisor, based in Bulgaria. Hi, Sue. Morning. And Pam Howitt is our senior technical advisor in Scotland. Morning, Pam.
Morning, everyone.
Great. So I'd like to introduce Chris Sanders, who's kindly accepted our invitation to join us today to answer any of the more difficult questions based on his experience. Research, climate and health program. So Chris, if you could tell us a little bit more about yourself and your experience, that would be great.
Hi, Al. I'm Chris Sanders. Having graduated in physics and meteorology, I worked for BRE in East Kilbride for 30 years on problems of condensation, thermal insulation, and so on. Then I went to the Caledonian University in Glasgow and ran a research group there on really much the same topics, the research on indoor climate and health it was. But I actually retired from that a few years ago. And I now run a consultancy business looking at moisture problems, thermal insulation, and so on. In amongst all this, for my sins, I was chairman of the BSI committee that dealt with BS 5250 for about 15 years. I'm sort of recovering from that slowly. Was also chairman of a couple of European standards committees dealing with moisture and climate data. So here I am.
Fantastic. So you are well equipped to answer any awkward questions or any interesting questions. So we'll just start with you, Chris. Actually, straight away, we have one, quite a general one from Coral on the YouTube feed. Just asking, do you feel the overall addition of moisture management to BS 5250 is preferred to the old control of condensation title?
Yes, I think it's better. We tried to generalize it. I think to think of condensation as a separate entity is a mistake. There are driving rain affects buildings, rising damp, and so on. And I think to think moisture holistically in buildings is much more helpful. I don't know whether people have seen the BSI white paper that Neil May and I produced 3 or 4 years ago, and that was really an attempt to broaden it and make it a much more holistic approach to moisture, and that has informed the current revision of BS 5250.
Chris, thank you very much. Pam, this is your first Proctor webinar, so welcome. I know the first was always a bit nerve-wracking, so don't worry.
Terrifying.
To you for one. So how do different uses of buildings and types of constructions affect the condensation within that building?
Yeah, it's a really good one actually, because you don't think that it's going to be much different than other ones. So really all types of buildings have a moisture load, which is more than often influenced by the occupants, what the building's being used for, and also what mechanisms are in place for that vapour and moisture to disperse. So if we look at the extremes of the scales, you've got maybe something like a warehouse that's used for storage. For example, building materials like our warehouse here at Blairgowrie. It's got large open areas, doesn't have a huge amount of heating, but it is very, very well ventilated by the roller doors being open all the time. And because it's being used as a store and there's not a lot of occupants in there generating moisture, any moisture that is there will be able to be dispersed very quickly. Mainly by the ventilation within that area. On the other end of the scales, you've got things like swimming pools or laundries. You know, they're very wet areas with very high degrees of moisture. The temperatures tend to be higher, which makes the air able to hold more moisture, which does mean that any small areas or any areas of cold bridging, cold spots, air leakage, etc., can manifest themselves quite quickly, and there is the increased risk of that warm, damp air meeting a dew point, so a cold surface, and meeting its dew point and releasing moisture. So in a warehouse, you have less risk of this. So you may not need a vapour control layer. You might not need something quite as high specification. But in something like a swimming pool, without a doubt, you need to put a vapour control layer in there, and probably a foil-faced one, and be very, very particular about your design, where you place your insulation, etc. Because you don't want to get any damage to your property. Aesthetic is your least problematic one. But you know, you don't want damage to your structural elements by hidden moisture within that building.
Okay, that's lovely. Thank you very much, Pam. And Chris, there's just a general sort of comment on here. I wonder if you had anything additional or any comments on the comment. So HDRB has said it's important to note that the results from an analysis to BSEN 15062 can vary significantly from analysis using the Glaser method. Do you have any comments on that?
Oh, well, yes, that's certainly true. The Glaser method is very simple. It just allows for simple heat transfer and vapor diffusion through the materials on really a steady state climate, whereas BS 15026 which is really implemented in WUFI, which we keep hearing about, that is much more complex and takes account of liquid moisture storage in materials. It takes account of the sun shining on the roof, the rain battering the outside of the building, and provides a much more comprehensive idea. For some constructions, say a metal roof with mineral wool, they should be much the same, the answers from the Glaser and WUFI. But for something like, say, a masonry wall with internal insulation, the Glaser method can't really cope with that at all, and you need something like WUFI, the EN 15026 method.
Okay, great. Thank you, Chris, for that. Appreciate it. And Sue, if I can come to you for one here, please. Simon has said, I always specify an internal vapor control layer. However, I think I'm picking up that this may not be needed with Wraptake. Is this correct?
Yes, it may well be correct. Typically, the vapor control layer performs functions, so it will help obviously control the path of vapor construction, but it will also act as your air tightness layer as well, just by the nature of the materials. So when using Wraptake on the external, for example, as your air tightness layer, taking the rest of the construction into consideration, which we would do, we look at the construction, we would either do condensation risk or WUFI, depending on which was most appropriate. And then we'd be able to advise then if it was the case that you did not need that separate internal vapor control layer.
Okay, lovely, thank you. And Ian, Joseph has asked, in your webinar, you discussed the BS 5250 changes in terms of pitched roofs if approved. Will this mean I don't need to install eaves and ridge ventilation in my pitched roof design?
Okay, thank you. Morning, everybody. Chris, you probably know this subject pretty well. I think this is probably part of your pains of BS 5250.
Yes.
Late or not. Yeah, for the first time, the draft of 5250 shows that you can use a pitch roof without traditional eaves and ridge ventilation by using what they call an APLR, an air permeable low resistance underlay, of which obviously Roof Shield is one. So it shows the proposal for that. It must meet certain criteria in terms of its permeability and its vapor resistance. But if you can specify APLR in your roof, that will provide enough air movement and vapor resistance to reduce the condensation without any additional ventilation. So yeah.
Okay.
Yes.
Does Chris agree? Does Chris?
Yes, I would agree with that. Yes, I mean, as Ian implied, has been a lot of controversy about this issue, but with the air permeable membranes, that would give you a degree of comfort. You should always ensure that there aren't any major gaps in the ceilings so that air can leak through. Warm, moist air from in the house can leak through into the roof, because that can be the major source of problems. So with a good ceiling and an APLR, you shouldn't need to ventilate the roof.
Okay, good. Pam, if I can come back to you, there's just a general question that you might be able to answer, then I've got another more complex one from Dylan. But first of all, I think someone else may have answered this. I'm trying to follow the YouTube feed. There was a general question about how long would a WUFI calc take, which I think kindly someone said, look, it depends how complicated your model is. Would you agree with that?
Yeah, absolutely. I mean, if you've got quite a simple wall, that could take, you know, a couple of minutes, and obviously depends on how powerful your software, your hardware is. But the more complex, the longer you run it to try and make sure that everything meets equilibrium, or studying it for length of times, it can take a long time to run them. And also you're then going back in and you're changing parameters with it. So you're looking at different assessments. So yeah, I mean, it could be anything from 10, 15 minutes from input to a report. You could be looking at a lot longer if it's very complicated, or you're looking at modelling quite a number of different assessments and solutions to get the right one and analyse it properly.
Great, okay, thank you. So the second question I had via email from Dylan, I'm doing a deep retrofit on my property, which is listed, so I can't put external insulation on it. We see a lot of those in Scotland and elsewhere, and currently it is stripped back to the bare walls. What suggestions would you have or make to improve so the overall energy efficiency is improved without causing any risk from moisture? Okay.
Yeah, I mean, I think quite a lot of us have those types of building. I'm sitting in one at the moment. Yeah, there's a few options that we've got that could be suitable, but one that's likely to be quite a good fit could be the our products Wraptake. Mm-hmm. So this is a combination of two of our most innovative products, our Wraptake airtight vapor permeable self-adhesive membrane, as well as our very thin, very permeable, very highly insulated product Space Therm. So these are bonded together, and that could be used on the face of your existing wall to improve the airtightness of your building, to reduce mitigated heat loss, things like drafts, etc. Mm-hmm. And you'll get a degree of reduction in cold bridging by that layer of Space Therm as well. So that means that you can then put a frame directly onto your wall and fill that up with an additional amount of insulation as appropriate for your building. And that will help enhance that nicely. And you don't need to worry about any risk of condensation forming, because both those products are very, very permeable and can pretty much be considered vapor neutral within the construction.
Okay, lovely, thank you. Chris, John has asked via email, is it better for an insulation to be vapor open or vapor closed?
That depends on the circumstances. I would have to say it would depend on the circumstances. In many constructions, a vapor closed in internal insulation on the wall, vapor closed would be better, I would say. In a metal roof, vapor open might be better. I don't think you can really say for any in general whether it's better. You'd have to consider each individual circumstance and look at the detailed construction.
Great, that's good to hear, because you do come across some in the industry that are very sold on a particular type of insulation, and
oh yes,
you know, and so it's good that every different scenario should be considered. Good, and another one, Chris, that's come through on the YouTube feed, if I can ask you. I'm not sure if this is a bit incorrect, but perhaps you can give it a go. There appears to be a discrepancy between BS 5250 and 13788 in the humidity class for low and high occupancy dwellings. In 5250, dwellings are class 3 and 4, but in 13788, they're class 2 and 3. Is that deliberate, and what takes precedence when completing glazer calcs?
I would say BS 5250 should take precedence, as that is more recent. The most recent 13788 is 2012, whereas, well, the current one is BS 5250 is 2016, and there will shortly be another one coming out. We're grinding through the process now. So by end of this year, early next year, there will be a new edition of 5250. So I would go with that, as it's more recent.
Perfect. Okay, that's great. Sue, I've not spoken to you for a while. Joe has said there's a steel beam in my roof construction which is causing a cold bridge. I cannot insulate it with traditional insulation. What do you recommend?
Okay, so we'll have a fairly straightforward but very efficient solution by using one of our SpaceThem products. We have different SpaceThem products which, depending on the scenario, it could be a case of using blanket or Wraptake to wrap your steel, or a cold bridge strip, which is cut specifically to the width of the steel that you're trying to actually cut out that cold bridge, and that's quite easily applied using a double-sided tape system. So we'll certainly have a solution. If you want to forward the details to us, we can have a look at it and be specific.
Okay, and I've got another one in from Marty, who's actually asking another product-based one, if I can stick with you, Sue, if that's okay. Mm-hmm. He's designing a high-rise building at the moment, so there's some project details there, but so where fire is a consideration, do you have any suitable membranes?
Yes, we do. There is, there's obviously quite specific requirements in high-rise for membranes which have to meet a certain reaction to fire classification, which is BS3D0. We have a range of membranes, whether they're vapor permeable, vapor tight, airtight, that will all meet this requirement, this reaction to fire requirement. So yes, we will have a solution in a membrane format that we can supply.
That's lovely. Thank you very much. Ian, and then I'll have a couple more for Chris, I think. So Ian, Kirsty has asked, light gauge steel seems to be increasing in popularity. Do you have any comments on their use?
Yeah, it's good to get a question on light gauge steel, because we are coming across it more and more, especially in medium and high rise buildings, with a sheathing board on top of it. Fundamentally, it's a good system. There's lots of advantages of it. It can be, you still have to follow the basic principles of keeping the building dry during construction. It's very important. You ensure that it's robust against weather from the wind, especially in the high rise. So in this case with Wraptake being self-adhered, it can be very good so it doesn't flap about. You ensure that it's vapor permeable, so it's still breathing throughout the life of the building is an important factor to take into consideration. And looking after the air tightness is very important as well. And that's one of the reasons that people are using Wraptake in this example, because they can use the Wraptake on the sheathing board, so it's got the permeability, keeping the building dry, and it's breathable for the life of the building. One of the easiest way of reducing the condensation in these types of construction, which is quite common, is to put the insulation on the outside of the sheathing, and therefore you're taking the dew point into the cavity out of the building, and it's a good system. So these are the things you should be considering. It's going to be included in the new 5250 draft that shows that kind of system.
Okay, good. And Ian, while I've got you, sorry, Dave has asked a couple of questions on YouTube regarding the sections holding the insulation blocks in place. So a U section holding insulation in place, the other layer. Can you tell us anything more about that detail?
Yeah, I saw the question coming in there. I'm not quite sure of what is meant by holding the insulation in place by the diagrams. The diagrams were from a plan view, so they were just held in between the metal studs, the insulation, so it wasn't held up in between. He also mentioned stick pins. Now, this gives me an opportunity to do a prop here. We've got stick pins here.
You just had one at home. You just had them.
Well, to be fair, I saw the question, so I rushed out to my car because I was on site this week looking at stick pins. So I showed some examples. I'm very jealous that my colleagues have used props in the past. So yeah, you can hold it with stick pins. They're very useful to hold the insulation in place. And if you're putting a breathable membrane on the outside of that insulation, it's certainly the best way to go. So I think that answers the question, but if you would like to contact us to clarify further, then we can do.
Okay, good. And sorry, Ian, last one. Roland said, isn't there a general condensation risk within the external wall at the upper floors of a building due to stack pressure when adopting an external VCL, e.g. Wraptake? So maybe you want to clarify exactly what Wraptake is for airtightness purposes. Okay.
Well, first of all, obviously, Wraptake's not a vapour control layer, it's a vapour permeable membrane. It's used for its airtightness, so it can be used in similar circumstances, but it's used around the outside of the sheathing to provide airtightness. As we mentioned in the seminar, stack effect is something that you should take into consideration, and taller buildings will have an increasing issue with stack effect that you have to take into consideration. Again, we can do calculations on that, roofing calculations. What we generally tend to find is that people might use a vapour control layer on that building, but they won't change the specification depending on its height. So if they use the vapour control layer at the bottom, they'll use it all the way up, taking into consideration what the vapour pressures are on that.
Okay, thank you, Ian. Chris, HDR has said on the YouTube feed, one of the limitations that I find with WUFI's implementation is that it's not very efficient at running a sensitivity analysis on constructions. And if this was made easier, it could speed up analysis. Do you have any comments on that?
Well, I would agree. It's as the other lady was saying earlier, Pamela, it is quite a slow process to run WUFI, quite complicated. And if you want to look at a range of different variables, you have to run WUFI repeatedly so to get a different answer. I think it's a very useful thing to do, though, because rather than getting one magic answer from WUFI, if you can vary the parameters you put into it and see which ones are therefore important. But I think the only way you can actually do this practically is to just run WUFI again with different climates and so on.
Okay, that's great. And another Chris has actually asked on email, thermal bridging is increasing in importance. What's the best way to calculate this? Can you take both heat loss and condensation into account in this calculation?
Well, you have to use appropriate software to do a two-dimensional calculation of the heat flow through the building component. There are a range of packages available, some of which are easier to use than others. There's Heat, American Software, and Therm, which I think at least one of them you can get free from the internet. The market leader, the Rolls-Royce, which I have been using for literally 35 years, is software from a Belgian company called Fisabel, called Trisco. That's fairly expensive. If you buy it now, it'll cost you about £2,000 to buy the package. So you have to be fairly serious commitment for this. There are various catalogues of thermal bridges around, which you can see if your construction looks like that and take the values. But all these packages both calculate the heat flow, which gives you the psi value, which is referenced in the SAP calculation, and it also gives you the surface temperature, which is the F value, which gives you the condensation risk. But there isn't really a simple back-of-the-envelope calculation you can do.
Okay, that's great. Thank you very much. Pam, Jasper has asked, what can I do to make sure I don't have any issues with interstitial condensation in my existing property? I've read some really scary stories about walls getting too damp from putting foam insulations internally. Am I better using external insulation?
It's a great question. I think it's something that if people go in and search on the internet, they find that out and hear them. We've sort of talked around it quite a lot. We obviously discussed it with the WUFI analysis in the actual presentation. Chris has touched on it as well. I think Ian's mentioned it too. I mean, moisture is one of the biggest things that can adversely affect your structure. Obviously, making sure things like the external maintenance is up to, maintained. So things like making sure your gutters and your downpipes are unblocked and aren't leaking, ensure your pointing is in good condition, flashing, etc. Do that before you start on any upgrade, otherwise you could be just wasting time. Thermally, it's in an existing building, it's probably not so much what insulation you use, but ensuring that the correct balance is considered. So you don't want too much insulation on the inside, for example, internally, which might then mean that your actual wall is terribly cold and it can actually start acting like a reservoir and hold on to moisture. So maybe in that situation, something like a thinner, more permeable insulation, like our Space Therm range, is a more, a better, healthier option for your wall, because that will allow some vapor movement both directions and some heat from within the room to touch that wall. Obviously, this is where WUFI is ideal because it can be used to assess those risks and make sure that you get that balance of insulation to moisture right. I know that on paper, external insulation is good, but there are parameters around not being able to use it. Personally, because I'm always dotting in and out the house, I like internal insulation because I want an instant response from my heating. I don't want to be heating up my wall. So to me, IWI all the way, balanced properly.
Well, I don't mind that you're slightly biased. No, you're not slightly biased.
No.
Okay, great. Now there's a couple of questions here from Steve. So I think what Steve wanted sort of a statement, then a question. I think what he's trying to ask, Chris, if I can come to you, is basically what's your opinion on the effects of ceilings on dew points and moisture contents in the roof structure?
Right. Well, if you, as I mentioned earlier, there's water vapor, heat and water vapor is produced in the house, and it has to escape by ventilation largely, and some of it goes through the roof, through the ceiling, and most of this goes through by air motion through holes in the ceiling. About 80% of the moisture that gets into a roof is being carried by air currents flowing around the hatch, around the lights, and so on. So to reduce the risk of condensation in the roof, it's really important to make the ceiling as airtight as possible. And there is a whole BS on this, which I should remember the number of. It's very similar to BS 5250. It's something like BS 5850. Sorry?
Is that for ceilings?
Yeah.
At 9250?
I think that's right. Yes. Yeah. Thanks, Ian. That gives comprehensive advice on how to make airtight ceilings. I mean, this also saves energy from the house as well, having your ceiling as airtight as possible. But provided the roof is well ventilated, or you have an AP, one of the membranes you were talking about earlier, there shouldn't be any risk. There shouldn't be a dew point in the roof.
Okay. That's good. And Chris, someone's asked, where can they get access to the consultation document for BS 5250 2020?
From BSI, it's appeared on their website. I was just wondering if it's actually out. It must have only just appeared. I can send you the link. I think is the best thing to do.
Okay. If you send it to us, and then the individual, I'm not quite sure the name, HGR, if you email Webinar Proctor Group, we can make sure that we get that to you, or Ian or Pam or Sue may.
Yeah. Yes, as I say, it's probably going to be coming out. If it isn't out now, it'll be out very, very soon.
Okay, and another question from Oscar. He's asked, can you recommend some good books on this topic or any further reading?
Oh, that's complicated.
Not necessarily on BS 5250 just, or maybe around the whole condensation type. Again, I would have to think about that, and I can email.
Well, maybe, Chris, there's a gap in the market for a book to be written.
There is one that Professor Hugo Hens in Belgium produced a few years ago on building physics and moisture problems, which was extremely good. It was translated into English. That's so whether you can still find it, Hens, H-E-N-S. That was a very comprehensive book. I don't think there's anything else. I mean, there's the BSI white paper, as I mentioned, which I think you can get free from BSI.
Okay.
A comprehensive overview of these things.
Great. And sorry to keep firing them at you, Chris. I have another one
okay.
From Nick. You're specifically mentioned by name. Do you have a view on the reasonableness of warranty providers requesting much more onerous boundary conditions than detailed in BS 5250, i.e. whole winter average external temperature of -2 degrees?
Yes, that is a real nuisance, I think. People do ask for very unrealistic conditions at times. I mean, the advantage of WUFI is that you can put in hourly temperatures, real outside weather data, and get a proper assessment. Whereas if you put in a whole winter of -2, that would never occur in the UK. You get sometimes ridiculous requests. I was involved in a building where it was a bank building, and they had to say that if the temperature was the coldest temperature that had ever been recorded in a particular city, and the building was full and the air conditioning had failed, there should be no condensation risk. And so that building was grossly over-designed. They wasted huge amounts of money trying to meet this. So they really ought to consider proper, realistic boundary conditions. I fear that sometimes people want boxes ticked just to cover themselves without appreciating that these can cause a very large amount of unnecessary expense in design and construction.
Okay, great. Thanks, Chris. So we're just coming to the last 2 or 3 questions. So if you have any more, please post them now in the YouTube feed. I've got one more by email, one more on YouTube. So now's the time to post any additional questions if you can. So Ian, this is something you're very familiar with, your experience. So what about off-site construction moisture risks, Paul has asked? So quite a generic question. Anything to consider there?
Yeah, that's another good subject to deal with. Again, BS 5250 has furthered its remit in looking at SIPs and CLT forms of construction and the moisture risks involved with that. Now, off-site construction has the benefit that there's usually less construction moisture because a lot of it's dry trades. So the main issues that you're looking for with off-site construction is keeping it dry during construction from rain, with driving rain more importantly, and what is the moisture risks during the lifespan of the building, and what's that, as we've talked about earlier, what's that moisture load? What are the people doing inside that building, and what is that condensation risk? So off-site has the benefit of less construction moisture, and they take into consideration the driving rain. So I think that answers the question there.
Okay, thank you, Ian. And Sue, a product-based one, if you don't mind. And in fact, maybe you could expand on this a little bit. So the question asked by Amir was, does Wraptake give any thermal benefit? Could you cover, just as we've been talking about off-site construction there, could you cover very briefly as well, after answering that, just any benefits of Wraptake in the off-site construction sector as well for us, please?
Yeah, absolutely. Wraptake itself will not actually improve the overall U value of an element, for example. However, what it can do is, because it improves the air tightness, your SAP and SBEM calculation will take that air value into consideration. So what that will do is that will reduce, obviously, the emission rate of the building. And in turn, what that then can do, as we saw in the webinar, is you can potentially reduce the amount of insulation that is then required in order to meet your target emissions. So indirectly, it will help with the overall actual thermal performance of the building, but in itself, you don't attribute any thermal value to the membrane itself. On retrofit, for example, or refurbishment, the fact it is air tightness will improve it will reduce the effect of draft on the building. So that will give a degree of thermal comfort to the residents. So from that point of view, in off-site manufacture, the advantage of using Wraptake on that position is, obviously, it's installed off-site, so you can install it very, very cleanly, for example. The advantage of it being self-adhesive means as well that during the transport, it's less likely to get damaged, during the actual transportation and actual erection on site. So that's a couple of advantages in those scenarios.
That's great. Okay, thank you very much, Sue. So last couple of questions. Chris, I have one here which I think would be suitable for you. Let me just find this here 1 second. Bear with me a minute. In fact, I think it came in through email. That's why I'm struggling to find it on the YouTube feed. Okay, here we go. So from Rob, there are some mixed views on whether hybrid flat roofs are suitable, given that they present challenges with the higher possibility of interstitial condensation. Do you have any comments on that, Rob? And then maybe we can come on to maybe a product solution from Ian, for example.
I have to say I'm not sure about that offhand. Have to look at that and see the specific design and decide what the problems were. So sorry to be vague.
No, that's fine. The secondary part to his question was, Ian, are there any membranes that can help address this to take a safe approach, or better to just specify a warm roof? Is that one that you can help with there?
Sorry, could you say that one again, Keira? Sorry.
Yeah. Are there any membranes that can help address this? So mixed views on whether hybrid flat roofs are suitable, given that they present challenges with the higher possibility of interstitial condensation. Are there any membranes that can help address this, or is it best to take a safe approach and just specify a flat warm roof?
I guess the problem I'm struggling with there is what they mean by the hybrid flat roof. I was busy scrabbling away there looking at 5250 because they have a new edition which shows a flat roof and a pitched roof together. I don't know whether that's what they mean by the hybrid flat roof. Flat roofs are difficult. They can be a good solution. In terms of condensation, the inverted roof is usually the best option, depending on the construction. Warm roofs, again, can be very good, but they have to just be designed properly with proper use of vapor control layers, etc. So I'm sorry, that's not exactly necessarily what they mean by the hybrid flat roof, but if they could clarify it further on the YouTube feed while we're still on air, or contact us later, then I'm sure we'll be able to help them.
Yeah, probably more detail by email. So I've got a final question. So I started with you, Chris, so I will end with this final question for you, please, from James. What implications is the revision of 5250 likely to have on diagnostics on conventional existing residential buildings?
It'll make them more rigorous, clearer. It will make it clearer what you need to do. I don't think there'll be anything terribly new in terms of the diagnostic techniques, but it'll just mean that things will be more formal. You'll need to check more things and be more careful when assessing the building. But as I say, I don't think there will be any huge step changes in things that have to be done.
Okay, great. Thank you very much. We have come to the end of all the questions. So some really good ones, some challenging ones, as we saw. So that's not a bad thing. That's always a good thing. So we love having all these questions in. Thank you very much to the technical team, and especially to you, Chris, for joining us. It's fantastic having someone with so much experience and also an outside view able to help some of these questions. And I've got no doubt they will prompt more, because we often get a lot of questions afterwards. So we will try not to hassle you too much, but we might send a couple of things your way. So thank you very much appreciated. And for everyone else watching, you can go to our website, www.proctorgroup.com, and /webinar is where you'll find, again, all the information to request a sample pack, which will cover a lot of the products that we spoke about today and the general concepts we spoke about, an introduction to this type of information. You can also request a virtual meeting with our sales team, who are working at home, of course, like most. And you can request your CPD certificate there and download it, and we'll then email you out a personalised CPD. So don't forget, our next webinar is in 2 weeks, Friday the 7th of August at 10 AM, which will be another live Q&A following the educational webinar, which is on pitched roofing design considerations, and that covers energy, moisture and air permeability. So some of the topics that we touched on today regarding air permeable, low resistance underlays, air tightness and different roof considerations. I think we'll be doing a bit more work on the hybrid one prior to that one, perhaps, Ian. Which is great. So yeah, another really probably more in depth, on that specific application. So please join us in 2 weeks at 10 AM on Friday, the 7th of August. You will receive a quick follow-up email to this, which will have a survey. Please fill it out. Be kind to us, but also be honest. So constructive criticism is welcomed. We read it all. I read them all. And if you have any specific requests, you can also put that in there rather than emailing us if it's easier for you, whatever you like. So I think that's it. I hope everyone has a lovely weekend. Thank you very much for all the questions and all the comments on the YouTube feed. It's great to see a bit of communication between attendees, and it's always lovely to see the thanks, comments, etc. So don't forget to subscribe to our channel, thumbs up on the video, all helps us. Share the positive feedback with the rest of our team, and thank you to marketing for producing yet another fantastic webinar. I know a lot of effort goes into these, so well done, guys. I'm sure you're watching, making sure it's all going well from a technical point of view. So have a great weekend, and thank you very much again.
Bye-bye.
Bye.
Okay.